Good afternoon, everyone. Or I guess not quite afternoon, morning-ish. Uh, Today, there are a lot of questions about proofs, so we want to talk about why we want to prove things, and I want to go over some examples of the process of what that actually looks like when you're approaching an unknown question versus sort of like how it goes through until the end. Uh, and I want to answer questions. There are a lot of questions this time, which is good that people are using this. In terms of agenda for this week, I want to note that there is a quiz on Wednesday where you'll have to write up a couple proofs. This is really in preface to the fact that there is a test on Friday that's going to cover through the end of the videos that are posted for week 2. Do note that videos are labeled by week, so I've said this a couple times, but that sort of tells you where you should be. So by the end of this week, you have to be fully competent with everything that's posted in the week 2 playlist. The week 3 playlist will start going up this week because I have to record it starting today, but you don't have to start viewing those until we get to the relevant piece. Okay. The quiz Wednesday, just to reiterate, is going to be a couple proof questions, and the real point of this is for you to turn in proofs in a test-like setting so that I can give you feedback back right away on Wednesday so that you have time to make adjustments before the test, and so that you have time if you want to meet with me in office hours on Thursday or what have you in order to make sure you sort of get down all of these skills, because again, because of the 7-week format, we have to sort of blaze through this stuff. So I want to give you as much opportunity for feedback and discussion as possible before having sort of going straight into tests on things. Hey, are there any questions about the agenda of sort of like how things are going for this week? Just so that that's clear. And then the next test will be Monday, December 21st. December 21st. So that is the last day of classes before the winter holiday break. So you can plan on these. And roughly speaking, where I said sort of like the first piece of the course was that we're going to go over all of the proof methods and learn to write proofs, this test will cover all the proof methods. This will cover just direct proof and proof by contrapositive. The questions before the quiz on Wednesday. I mean, you didn't get the questions before the quiz last time, did you? I'm not quite sure what you mean by that. Oh, yes, sorry, you can ask questions. Yes, absolutely, you can ask questions before the quiz on just like last time. All right. Yes, yes, I figured it out. Okay. So I wanted to start just before we talk about proving things with just saying a couple words about why we prove things. And I've given you sort of 2 readings about this. So we talked about, I guess the Fermat's last theorem one wasn't a reading. The Fermat's last theorem was a video. But we talked about this idea of Fermat's last theorem, and people wrote a bunch of very intelligent and interesting responses to this. A lot of people seem sort of struck by the complexity of the proof. A lot of people mentioned how at the end of the video they sort of show you flipping through the actual proof, which is something like 300 pages. But that's really a lie, because in order to understand this 300 pages, you have to have understood thousands of pages of other math that this is based on. So there's this whole idea of like building this really, really, really complicated building this really, really complicated structure out of these individually very simple blocks. Because ultimately everything in this proof and in every proof is sort of a combination of just these basic logical operators that we've been talking about. It just happens that it is a very complicated structure out of simple blocks. But thanks to the hard work of Wiles among hundreds, if not thousands, of other mathematicians, we now know that this statement is true. And one thing that's really nice about this is as long as you trust the broader mathematical community to verify this, you don't have to read the proof to know this fact that Fermat's last theorem is true. You just have to believe that Carl Rubin and Shimura and all of these other people who read it know what they're saying. And so we have this idea that sort of this is part of the things that are true. Okay. And ultimately, all academics, be it math or science or literature or whatever, it's all the search for truth. And so in the mathematical sense, this is our truth. This is a thing that is true because it's been proven. Okay. So why are these proofs important? Well, this goes back to the Richard Guy piece that you read this weekend that gives you all of these examples to show you that patterns can be incredibly misleading. And so you might expect that, oh, if I check Fermat's last theorem in a few cases and it seems to be true, then it's probably true. But hopefully this reading did a good job of disabusing you of the notion that if you collect a bunch of evidence of something, then that means that it's true. Sometimes you can collect a whole bunch of evidence of something, and it turns out that it's not true. The smallest counterexample to a claim can be absolutely preposterously large, and this is a thing that really happens. Okay. So, sure, it's great to collect evidence of things, and we'll talk about that as part of our process, but ultimately, if you really want to know something is true, you have to prove it. Okay. But on the other hand, and a lot of you commented about this in the Fermat's last theorem response too, the magnitude of the power of the thing you've actually proven is actually quite remarkable, because once you have this proof, then you actually know this result that's true for infinitely many exponents and infinitely many x, y, and z. And so you get this really potent thing out of this finite amount of work. Granted, it's a large finite amount of work, but it's a finite amount of work that gets you an infinite amount of information. Okay. And so usually the idea is that the yield from a proof is much larger than the work that goes into it. Namely, you usually get an infinite amount of information out of a finite amount of work. And so that is very spectacular and helpful. Okay. So a lot of people in their questions asked if I could go over the proof process. And so I'm going to attempt to go over what I consider the process for a typical proof question, and then I'll do an example where I'll sort of model that for you as best as I can. Okay, so okay. Now, please note this is not an algorithm. In no way will all proofs follow this outline that I'm about to show you, and depending on the question, this outline might take 20 minutes, or it might take a whole lifetime, depending on the question that you're going to try and prove. Okay. But this is just a rough idea of how you proceed through one of these questions. So in real life, most questions you encounter are prove or disprove questions. Okay. So I'm going to, as I discuss this, assume I'm talking about a question where I'm given a statement and I'm asked to prove or disprove it. Okay. And what this really means is decide if the statement is true or false. Okay. And the idea here is if the statement is true, it must be provable. And if the statement is false, then we should be able to find some sort of counterexample or in some other fashion show that it's false. Provide a proof of that or whatever. Okay, so the first thing I will always do when looking at a statement that's of this form is to try and find examples. Now, I want to emphasize, this is not just something I do when I'm teaching this class. This is something I do all the time when I'm working on research, because ultimately all math research is finding interesting statements and deciding whether those interesting statements are true or not. And so usually, of course, you're hoping that the interesting statement is true, but you've got to decide what the statement is and that it's true and all of these kinds of things. And so this process of prove or disproving something is basically what mathematical research amounts to. It's what Andrew Wiles was doing with Fermat's last theorem for a decade. Okay. But to start with, you want to try and find examples to make sure you understand the statement. So if you can't find examples, then it might mean that you don't actually understand what the thing is saying, which is a serious problem that you should rectify before you can continue. Okay. Now, of course, as you go about finding examples, you might get lucky and you might just happen upon a counterexample, in which case then you're done. But you might not find a counterexample, and you might, through the process of spending 5, 10 minutes, however long you wish, of trying to find examples, you might convince yourself that you actually think the statement is true. And if you think the statement's actually true, then you want to enter what I'll call the scratch work phase. Okay. This is where you write stuff down, and I would write it down on paper. I really recommend that. But you're welcome to type it if you prefer. But for the scratch work phase, I would write it on paper because I can write faster on paper. I can see it better. It makes things feel better. I don't know. It works better for me. That's what I'll say. Okay. So you write a bunch of stuff down. What kinds of things are you writing down? Well, you're writing down all of the things you know. So you're writing down definitions. You're writing down implications that you see. You're writing down any theorems that might apply. You're probably writing down things like the contrapositive of the statement you're trying to prove. etc., etc. You're writing down basically everything you can think of that might possibly be part of a proof. Okay. And so the way you can think about this is, here's the place I'm starting, here's the place I want to end, and I'm trying to show that P implies Q. During the scratch work phase, you're sort of making lots of random jumps using the logic that you know. And eventually, out of all of this, you get to some path that actually gets you from once I have P, then I have Q. Okay. But the more complicated the thing you're working on is, and the more things you know, the more things there might be to try. And so you end up with this structure that's like, okay, well, I know this, and I know this, and I know this, and I know this, and I know this. And lots of the things you know aren't ultimately necessary, because ultimately your proof in this instance is just that piece. But there is no way to go immediately from P, or there's no way to go immediately from the problem to this one path. That's just not going to happen unless you've done the problem before. You're going to go in a bunch of directions and have a bunch of false starts. And so ultimately you want to do all of that on a sheet of paper, and then you want to reconstruct from this the proof that you find. Okay, so basically here I'm suggesting, here you're really making a rough draft in, and I recommend at this point, this is when you should start teching things. So you should do a rough draft of doing this thing in LaTeX. Okay. So that is of the blue path that I outlined here. Okay. So you deliberately want to, when you're writing this up, you want to ignore anything that was not part of your proof. Okay. In particular, unless you find a counterexample, the examples that you did that helped you understand the problem and helped you decide what to do, those are not part of your proof. Those you should not type up. Okay. And a lot of people are asking about this whole like want to show business. This stuff where you're saying like when you're writing and rewriting what the thing it is that you're trying to prove, this is really something that's going to happen a lot in the scratch work phase, where you're going to be writing to yourself, okay, it would be good enough for me to show this, or to show this, or to show this. And so this is really something that's going to occur most often in something that is happening handwritten during the scratch work phase. Usually you will not include this in a typeset version of the actual statement. Okay. Now, I should mention this is the optimistic vision of what happens, where you try all of this for a while and eventually you get it, and then you go up and write a proof. But that doesn't always happen. Sometimes you don't find a counterexample, then you try and find a proof, and then you don't find a proof. So you might have to go back to looking for counterexamples if you don't find a proof. And so it's quite likely to happen that you'll bounce back and forth between these first two phases for a while before you're really set on, I have a counterexample, great, I can write that up. or I have a proof, great, I can write that up. Okay. Now, even better / worse, once you get to this phase where you actually have a proof and you're writing it down, quite often you will find an error in your proof, at which point then you have to go back and start looking again. Okay. But provided you make it through writing up your sort of blue path here without finding an error, then the last thing you should do here is you should proofread your proof. Okay. And you're not just looking for the fact that the proof is correct. It should be. That's one thing to look for. But you're also looking for the fact that it's readable and well structured. Okay. In particular, you want to make sure that nothing that's unnecessary is there. And what do I mean by something unnecessary? When I talk about something being unnecessary, what I'm talking about is maybe you wrote down a definition that you didn't use. Maybe you wrote down an implication that you didn't use. And those kinds of things you want to make sure you omit from your final write-up of the proof. Okay. Now, we've just started doing proofs, so the proofs that we're writing now tend not to have a whole lot of steps to them. And so this process that I've outlined here may be much shorter than this outline makes it look. But still, you're responsible for thinking about all of this as you think through your various proofs. And you want to make sure, again, that every proof you write down is ultimately written in a way that is as simple and understandable as possible. Okay, are there questions about that? I do want to emphasize, by the way, none of this is saying that your proof should be as short as possible or as terse as possible, just that it doesn't include unnecessary things. Ultimately, everyone will have their own writing style, and that extends just as much to proofwriting. Some of you will write these really short proofs that will really carefully highlight every detail that's important without saying anything else. And some of you will prefer to write proofs that are a little bit more flowery, that explain things a little bit more clearly, and are a little bit longer. This is a writing style thing, and there is no one right way to write a proof. Very often, there will be two proofs that I give full credit to for something that one is 3, 4, 5 times as long as the other one. Both ways are okay. Just make sure that your writing style is consistent and clear and communicates to someone who's reading it everything they need to understand the proof that you've written. So someone actually asked in the questions whether there's such a thing as including too much detail. I think broadly the answer is no. You can include as much detail as you want. However, I do think there's a point where including too much detail can actually make understanding the thing that's been written down a little bit harder. Okay. So I would say use your judgment, but generally I'm not going to complain if you write too much to explain your points, as long as you're not including unnecessary pieces. Okay. Okay. So I want to go over this in an example and just sort of show you what these various phases look like. Okay, so here's the statement. If x, y, and z are consecutive integers, then x plus y plus z is a multiple of 3. Okay. So let's think through the things I said before. So the first thing I said was try some examples. Okay. In particular, when you try some examples, if you decide you don't know what a consecutive integer is, then you might have to look that up, and that is a good clue that something has gone awry. But let's say I try something like 7 plus 8 plus 9. These are 3 consecutive integers. If I add those together, that works out to be 24. So I'm going to put a check mark there to say, hey, there's 3 consecutive integers that sum to 24. I might try 1 plus 2 plus 3. That's 6. That's a multiple of 3. See, I might think, wait, it didn't say they had to be positive, so I might try something like minus 4 plus minus 3 plus minus 2. And I see that's minus 9. Okay, so that is a multiple of 3. Well, what if one of them is 0? I might try 0 plus 1 plus 2, and that's 3, so that's a multiple of 3. And so this is just the try examples phase. Okay. Now, how exactly long you want to go about this, that's up to you. At the moment, again, all of these things have worked out to be multiples of 3. So I might start to suspect, if this was me doing this, that this statement's actually true. I might also suspect, if I was watching this video, that maybe Tommy just knows where all the counterexamples are and he's just writing up a bunch of examples that aren't counterexamples to lull me into a false sense of security. Those are equally possible. But once we've done this, we can proceed on to the scratch work phase. So here, I have to really start thinking about what a proof is going to look like. So it's going to involve x, y, and z being consecutive integers. Let's see. I'm going to need to show something as a multiple of 3, so I will probably write down that multiple of 3 means there exists k such that x plus y plus z equals 3k. So really that's sort of like the want to show piece. And a key thing about both of these phases is that no one is ever going to see any of it except for you. or whoever you happen to be working with. And so you don't have to be precise. You don't have to use all of this careful language. You don't have to write in sentences or any of these kinds of things that I do when I'm writing up the examples for you in the videos, because those are meant to be sort of like, oh, if you turned this in, I would give you credit for this. This is not going to get turned in. This is just you trying to figure these things out. Okay. So as you start to write this down, you might hone in on the fact that you don't actually yet have a super precise way of saying what x, y, and z are consecutive integers means. And so you might try and figure out, okay, how do I write this? Okay. Well, what I might notice here is, okay, well, what this really means is that the gap between each of these is 1. So really what this means, I guess, is that y is x plus 1, and z is y plus 1, which is really to say that z is x plus 2. And now that feels useful, that I've been able to rewrite these things in terms of, that I've been able to rewrite y and z in terms of x. And so you might then write and so you then might say, okay, well now x plus y plus z is, and so it's x plus 1 plus x plus 2, which is 3x plus 3. And now this is looking promising, because that is 3 times x plus 1. And so if I look back to this thing I wrote up here that I wanted to show, what I really now have is that x plus y plus z is 3 times x plus 1. This is the thing I want to be k. And what I'm starting to see here is that in this sort of idea soup that I have here, I basically have all the pieces I need in order to write down a proof that this original statement is true. Okay. Now, if you turned in this as your proof, this would probably be something like 0 points or half a point or something, because this is not written as a proof. But all the ideas are here. So what we have to do now is we have to follow our sort of like Mad Lib format for a proof, as many of you quoted. And we have to actually write this up. Okay, so we have to write down a draft. Okay. So this is the point where I would recommend you start typing instead of handwriting. Okay. I'm still going to handwrite it, but I would recommend that you do this part actually typed. Okay, so you're going to start the proof. And so I'm writing down a proof here that if x, y, and z are consecutive integers, then x plus y plus z is a multiple of 3. So I need to start with, suppose x plus y plus z, or sorry, suppose x, y, and z are consecutive integers. Now, I sort of meandered my way through this before, but I can now jump right to the point. What does that mean about x, y, and z? Really, it means y is x plus 1, and z is x plus 2. So I can now write that. Okay. Now, once I've written this piece, I now want to think about x plus y plus z, because I've sort of seen that now x plus y plus z, something nice is going to happen. Okay. So, again, my usual wording here is to consider x plus y plus z. And so that is x plus 1 plus x plus 2, which is 3x plus 3. Okay, and now I want to make the observation that if k is x plus 1, then x plus y plus z is 3k. Okay. Again, I'm making that observation because I know I'm trying to put the pieces together here to get to the fact that x plus y plus z is a multiple of 3, which has that definition. And that was the k I wanted. Okay. And so, and I'm not going to write and so again because I just wrote it, so I'll write thus instead. Thus, x plus y plus z is a multiple of 3 by definition. And then I would put proof box. And so here's, I think, a part of what makes this different than other math classes you've probably taken before this. You've done all this work. All this stuff is written down, but none of this is getting turned in. Like, nothing on this page is getting turned in at all. You don't have to turn in this. The only thing that actually gets turned in is the blue part. And now I recommended that before you actually turn it in, you go through and proofread this and decide if maybe there was a better way to write some of this. And so I think that's always a good last step, is to sort of reread your proof. It really helps if you read it out loud to make sure that it sounds like English and that it makes sense and flows naturally and all of those kinds of things. But once you reread it and are happy with it, then you're ready to turn it in and go to the next question. Okay, questions about that? Okay, so let me go over some of the questions that popped up in the Katie question response, which people have been using well. Okay. So first question, do you need to write want to show in your proof, or these like subset things. Okay. So this want to show business, I would say usually not included in proofs. But it can be if you really wanted to. Rose asked about -1 plus 0 plus 1. That's 0. And 0 is 3 times 0. So 0 is a multiple of 3. So yeah, it works. But the asker also asked about using this in proofs. And yes, you should use this. And the place this shows up is in written proofs of set equality, just as a reminder. Okay. Where, remember that in order to show A equals B for sets, you actually write two proofs. One is that A is a subset of B, which you usually would write this and then some proofs. And then second, that B is a subset of A, which you would label this way and then write some proofs. I think this is very helpful structuring to the reader to explain to them what's going on. Okay. This is also true, by the way, for proving biconditionals. If you go to prove an if and only if statement, you need to prove both implications. So if you want to prove P if and only if Q, you need to prove P implies Q and Q implies P. And it is often useful in doing this to mark off the sections of your proof with those arrows. Okay. Note, for section labels, this is a perfectly appropriate time to use the implies and implied by symbols in LaTeX. I know in the homework I say don't use them. You can use these as section labels. Someone asks, when we're given a prove or disprove question, how do we decide whether to prove it or not? And, well, that's kind of the question. There's no set way to do it. If there was, then math would be easy, and this course would be especially easy. Because basically, once you've decided whether the thing is true or false, you've completed the question, once you've sort of rigorously decided that. So you really have to sort of take two paths at once in your brain. One path in your brain has to be walking towards trying to find what a counterexample looks like, and one path in your brain is looking towards trying to figure out what a proof looks like. And you know, at the end of the day, one of these two paths doesn't lead anywhere. It might be really long, but one of them is going to sort of dead end at some point, because either the thing is true or it's false, but you're never going to know right off the bat whether it's true or false. That's part of the fun and the challenge of doing proofs, is that when you're given a prove or disprove question, could be true, could be false, you'll develop some sort of intuition that like, oh, this is probably true, but Who knows? Might not be. It's very similar to in Calculus 2 when you did all of these questions about whether series converged or diverged. And sort of like there were tests to show something converged and tests to show something diverged. And over time, you maybe developed some sort of intuition for what test to use and what the answer was going to be before you actually formally did it. It's very similar with all kinds of proofs. You'll figure out sort of some inkling of how this works, but you'll still be surprised sometimes. Someone also asks if negation and counterexample are the same thing. And negation and counterexample are not the same thing. So a negation is something every statement has. Okay. Whereas a counterexample is something that only certain statements have. Okay. Namely, counterexamples are things that are only had by false for all statements. And in this case, even in the case where it is a false for every statement that has a counterexample, the counterexample isn't the negation, the counterexample is the proof of the negation. Someone wisely notes that if I write this in prose, it's very ambiguous what I mean. And they basically asked, should I just put parentheses to say, like, what I really mean is X is in A, or X is in B and X is in C? And it is perfectly fine to use parentheses in this fashion. And the reason here is that this statement and this statement with the parentheses that way and with the parentheses this way, these are different statements. And so it is possible, for example, that the first one is true and the second one is false. Okay. Questions about that? Someone asks, is it necessary to include an example in a proof? No, it is absolutely not necessary. Sometimes it is helpful I would say probably in this class you're never going to be writing something so complicated that you really need to include an example in the proof. Yes, May. You asked about avoiding symbols. It's only the logical symbols that I'm encouraging you to avoid. So that is, I'm asking you to avoid that, and I've never even said this, but that for and that for or. But it is perfectly fine to use equals, square root, is an element of, is not an element of, is not equal to, intersect, union, etc. These are all okay and encouraged. These I would discourage, including that or that or that. These I would avoid. So it is specifically the symbols that are substituting for logical words that I would avoid. This includes these as well. Because, well, it makes it messy to understand if you use both of these, and I would rather use these than these. Okay. Someone asks, is it necessary if you have a bunch of integers to give further explanation when you add or multiply them to say that the thing you get is an integer? And this is an excellent question. So, for example, if x and y are integers, we need to say yx plus y is an integer. Okay. And whoever asked this question, you're completely correct. We are actually saying something. We need to know something about the integers to know that if you add two integers, you get an integer. But for purposes of this class, I will say we're confident enough with how integer operations work that this does not require further explanation in this class. If x and y are integers, and for some reason you want to claim that x plus y over 2 is an integer, that you definitely need to explain, because you need to know somehow that x plus y is even in order to say that you can divide it by 2. But any pair of integers that you add or multiply or add and then multiply or whatever, that's going to give you an integer, and you do not need to justify that any further. Okay, so someone asks, in the homework, I often come across stuff like this. And I'll say things like this. And so the question was, where did this come from? And we sort of did an example of this earlier, actually, where when we were looking at this example, we sort of figured out as part of our scratch work what the thing was going to be. In this case, it was called k, but it ended up being x plus 1. This is something you can figure out in your scratch work. Or if it's something like this, you can probably do it in your head. If I want to say that 4k squared plus 4k plus 4l squared plus 4l plus 2 is 2 times something, what is that something? Well, that something is 2k squared plus 2k plus 2l squared plus 2l plus 1. Okay, there are some questions from specific homework questions, which I'll talk about in a second. But are there any questions about proof writing more broadly that people would like to talk about? Okay, so there are two questions about the homework, which are about 15 and 18. So 15 is this question about suppose m and n are doubly even, prove these things, and I guess this will also apply to 16, which also asks you to prove something about doubly even numbers. And it asks, do we have to write out both the definition of doubly even and the definition of even? And the answer is going to be yes, at least most of the time, because you're going to need to write out the definition of doubly even, which then has the definition of even in it, so you might also have to write out the definition of even and then unwind it back into the definition of doubly even at the end, depending on exactly what the question is. But most of the time, yes, you're going to have to write out both of those definitions. Certainly, both of those definitions will show up in the scratch work. If you're lucky, you might get to avoid writing them both out every time. Someone asks, for questions like 18, where we're supposed to prove multiple things, is it best to split them up at first? So 18 is asking you to show that these two sets are equal, A union B intersect C and A union B intersect A union C. And so what the question asker is alluding to, I believe, is this thing I mentioned earlier, that when you're going to show these two sets are equal, you really need to show that the two sets are each included in the other. So we need to show that the left-hand side is a subset of the right-hand side and the right-hand side is a subset of the left-hand side. And should you treat those separately, you should absolutely treat those separately. You want to basically think about these things completely separately, and then basically at the end of the day, your proof is really, here's proof 1, here's proof 2. You're really not going to gain anything by thinking about these together, and more likely you're going to confuse yourself. So you definitely want to break this up when you're thinking about proofs that really have two pieces. So mutual inclusion for set equality, or mutual implication for some if and only if sort of statement. Any other questions from the homework before I jump to other examples? Okay, so what I'm going to do here is write up a new definition. So this is sociable subsets. I'm going to write up some questions about sociable sets. And then I'm going to give you, we'll say, 15 minutes to look at these. So get yourself a snack, a coffee, whatever. And then we'll reconvene at 12:15 to talk about these questions. So I'll go through them all with you piece by piece, talk about what the thought process was like, answer questions about them. But I really encourage you to work on these over this time because there's definitely going to be stuff like this on the test. All right, welcome back, everyone. All right, let's talk through these examples to give us sort of a sense of how we can think about these things. So you'll see a bunch of these questions on the homework, and there'll certainly be one on the test and these sorts of things, where there's a definition and then some prove or disproves about it. And the first thing you usually want to do is sort of try and make sure you understand what the definition actually is talking about. So you want to write down some examples. And so there's no sort of super neat procedure to this, but you can take something like 1, 2, 3 and decide, does that meet this definition? And, well, yes, I could let x be 2, and then 2 plus 1 is in this set. Okay. So this is an example. Whereas I could also write down some non-examples. That's also helpful. And so I could write down something like 1, 3, 5, 7. And that's definitely not an example of something that is sociable, because none of these numbers have that number plus 1 also in the set. Okay. Make super sure you pay close attention to what the quantifier is in the definition. So in this case, that quantifier is a there exists quantifier. However, it may well be that what shows up actually is a for every quantifier, in which case then you need to handle these things differently. Okay. All right. So hopefully you wrote down some examples of this sort, just to get a feel for this and make sure you are comfortable with what this definition was saying. Okay. Next question here is the empty set sociable? And this is something that I mentioned because we've talked about this a bit. The empty set with quantifiers is weird. But in particular, the thing about the empty set is no existential quantifier is ever true for the empty set. So any statement that starts, there exists X in the empty set such that blah, 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 is automatically false. Okay. And so in particular, is the empty set sociable? No, because that would be saying that there existed an X in the empty set such that X plus 1 was in the empty set. Okay, so then what follows is 4 statements about sociable sets that we have to decide whether they're actually true or not. Okay. So here's the first one. If A is sociable and 2 is an A, then 3 is an A. And so we have to decide, okay, do we really believe this is true or not? Okay. And so you might look up at your list. Excuse me. Excuse me. So you might look up at your list of examples. Hopefully you wrote down more than one example. And say, okay, here's a sociable set where 2 is in the set and 3 is in the set. So does this example make this statement true? Question. So you can put yes or no in the chat. Does this example that we have here make this statement true? I see a lot of agreement that the answer here is no. And the answer here is no. One example doesn't make this if-then statement true. Because remember, when I start this, if A is sociable, then blah, 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 this is really a slightly hidden for every statement. This is a statement about every sociable set. And so the fact that it's true for one sociable set doesn't make this statement true. Okay. In fact, this statement is definitely false. Okay. I guess I should start labeling these so that I can match it up on my writing. But this statement is definitely false, and in order to show that it's false, I just have to give you an example. Okay. This is false. Okay, and so we'll disprove this by counterexample. Would anyone like to volunteer a counterexample? One, two. All right, 1, 2 is sociable because 1 is in, let's call this S. Okay. 2 is in S. And 3 is not in S. Remember, my negation here of this if-then statement is going to be a set, I guess I should have called this A, sorry. My negation here is going to be something where the if part is true, so that is where A is sociable and 2 is in A. So that is this set 1, 2, or 0, 1, 2 is also suggested by the chat and would work just as well. Where both these pieces of the if part are true, but then the then part is false. Okay, so we want this part to be true and this part to be false. And that's what the negation of an if-then statement looks like, is the hypothesis being true and the negation being false. And so that's why this is a counterexample. We got vast amounts of agreement for the first piece. Let's look at 2 now. Is 2 here true? So tell me, yes, it's true and we're going to prove it, or no, it's false and we're going to disprove it. Fewer people commenting, but both seem to say it's false. So what does a counterexample here look like? Okay. Again, a counterexample here looks like something where we have a set that is sociable and a subset of it. So we want this part to be true. And then we want this part to be false. Okay, this is for a counterexample. So I want to take a sociable set. Perfect. Yeah, that was almost exactly the example I was going to give, is what the chat gave me. So we'll disprove this by counterexample. And so the counterexample offered by chat is A is 1, 3, and S is 1, 2, 3. Okay. And then a similar example with minus 10, minus 9, and minus 8 also offered. Okay, so this is sociable. A is a subset of it, but this is not sociable. Okay, and so namely, when we wrote down what we wanted, we wanted a sociable set, a subset of it, and then we wanted that subset to not be sociable. This is exactly what we have. Okay. Now I want to remind you, I've said this before, but this is just a hint for life. Whenever you're giving a counterexample, give exactly one counterexample. There's some temptation to exposit more about why the statement isn't true. And so you might be tempted to say something like, this. Don't say something like this. Okay, and there's two reasons for that. One is this is kind of squishy because when you say might not be, you're sort of making a claim without proving it. But also, this is just infinitely more complicated than giving one example. Okay. So when you're disproving a statement, your mind should go straight to, I'm going to give one example. Okay. And it might even be fine to say, actually, this is a pretty coherent explanation of why this thing actually isn't true. But the nice thing is if you understand this kind of coherent explanation, it leads you directly to this one example or an example similar to it. And so you just want to give the one example. Okay. No one can argue with your counterexample. I mean, unless your counterexample isn't actually a counterexample. But as long as you're confident you have a counterexample, you want to give that and not say much more. Okay, so let's try another vote. So, is 3 true? Yes means it's true, no means it's false. Ooh, we have controversy this time. I have more than one of both yes and no. Okay. So let's write down, this is helpful, what would a counterexample to 3 be? A counterexample to 3 okay, so it would be sociable sets A and B so that A union B is not sociable. So, two sociable sets whose union is not sociable. Does anyone want to offer an example of two sociable sets whose union is not sociable? Okay, so what is the union of 1, 2, 3, and 5, 6? This is a suggestion in the chat. The union of these be 1, 2, 3, 5, 6. And is the set 1, 2, 3, 5, 6 sociable? Yes or no? Is this set sociable? It is sociable, right? Because, for example, it contains 2 and 2 plus 1. So that is an example, not a counterexample. Does the fact that this is an example tell me that this thing is true? Sorry, does that tell me that 3 is true? Right, exactly. Those of you who are saying, no, we have to prove it, that's right. Unfortunately, one example does not prove this universal quantifier. Okay. But it does perhaps give us a hint as to where we should look when we try and prove this. Okay. Because what this might actually do in the example is show us why it ends up being true. And particularly if you search for a counterexample for a while, you might see where the sticking point always is. Okay, namely, just in words, the sticking point is if you start with a sociable set, A, that means that it contains something and that same thing plus 1. Well, automatically those things are also put into the union. So the union is going to have those things just because A did. That's, in words, what's going on here. Okay. And so what I have to do when I'm writing down a proof is I have to write down a proof that basically summarizes those words that I just said. Okay. And so that's going to look something like this. Okay. So let's suppose A and B are sociable. Okay, I'm going to try and mimic this piece. So what I did here was to find a valid x inside of A. Okay, so by definition, exists x in A that x plus 1 is in A. Okay. But now, since x is in A, it's also in A union B. Likewise, since x plus 1's in A, x plus 1's in A union B. Okay, and thus there is x in A union B, such that x plus 1 is in A union B. Okay, and that exactly means that A union B is sociable. And so you can see here, I hope, sort of what this process of iteratively converging to a proof looks like. You look at the statement, you maybe think, okay, that statement doesn't look true. So you write down some examples. You write down carefully what a counterexample here would look like. And then you try and find that counterexample, and you try a few things, and you sort of see, after trying for a bit, sort of like what the basic point is of why this can't happen because of, say, this pair is always ending up over there. And then once you have that sort of seed of an idea, then you can try and write it down carefully, and then you end up producing one of these proofs. Okay. And then, of course, at the end of the day, the only thing you have to turn in is this part. And so all of the part where you wandered aimlessly in the desert trying to find a non-existent counterexample to this claim, none of that needs to be explicated or turned in or anything like that. The only thing that actually needs to get turned in here is the answer. Yes, so Rose, that's an excellent point. So the statement here said, if A and B are sociable, then so is A union B. When we actually wrote up our proof, we supposed that, but we never actually said anything about B being sociable. So really, actually, we could note in our proof, or we could extract from our argument the assumption that B is sociable. We don't need that. And so that is exactly the kind of thing that you can note upon revision, is that you don't actually need that B is sociable. So here, I would not complain. But if your proof that you turned in started like this, so if your proof starts off like this and then goes on to be the same as this proof, then I'm going to complain, because you've now introduced this whole extraneous piece with a y that just doesn't need to be there, and in fact is muddying the waters about what the proof actually is. Okay. So this stuff is extraneous. But this stuff that I've underlined is certainly stuff that you're going to write down in your scratch work unless you happen to like magically see the solution from the start, because you're going to think, oh, we were given this, so I'm going to write down this all of this information, and then it's just going to turn out that you don't actually need all of this information. Some of it is excess, and then that's what, when you're revising and editing your proof, you say, aha, this was not needed, so I can cut this whole words out of my proof, make my proof tighter and shorter and easier to read. Okay, are there any more questions about sort of like what you have to take out of this in order to make it correct? The key idea here really is that a proof isn't the answer. A proof is a presentation of the answer. And so all the things that would normally count in presentation count in proofs. It's not just, is this technically the answer? It's the explanation of the answer that matters. Okay, so 4 here asks if it's true that if A and B are sociable, then so is A intersect B. Is this true or false? We have loud agreement again. We have an awful lot of people writing that this is false. Okay. And so that must mean we're going to write down a counterexample. Okay. And again, just to reiterate, what is a counterexample going to be? A counterexample here will be sets A and B that are sociable. But where A intersect B is not sociable. Okay. And remember, this showed up a couple times on the quiz, which, by the way, if there's any questions about stuff from the quiz after class, I have office hours, and I'm happy to talk about any of the questions from the quiz that people want to talk about. But I just wanted to mention, anytime this word but shows up in a situation like this, this is really just a way to say and that sounds prettier in this particular instance. Because what you're doing with the word but is you're establishing a contrast between the thing before it and the thing after it, and that's purely aesthetic. It's just saying, hey, isn't it cute that this thing at the end is kind of like this thing at the beginning, but not exactly. It's actually kind of the opposite. But in terms of logic, that aesthetic contrast you're creating doesn't mean anything. It's just saying the thing before this is true and the thing after this is true. So the word but here is really just being used for aesthetics, for making the proof or the wording look nicer. Okay. So does someone want to volunteer a counterexample here? Let's see. Someone suggests 1, 2, and 2, 3. Right. And so this is a great counterexample. So great, in fact, more than one of you came up with it. So here is a counterexample. And so these are both sociable. But A intersect B, which is the set 2, is not. Okay. Well, let me give you a variation. Okay, so here I'll give you one more question about sociable sets before you probably never think about sociable sets ever again, where I'll take sort of a refinement of the previous one. So the counterexamples people gave me failed because the intersection of the two sets had only one element. What if I guarantee instead that the intersection has at least two elements? Will this be true? And I'll give you a couple minutes to think about this. I see one vote in the chat for still false. Let's see if other people have votes. I'm happy to entertain additional votes. Have another vote for false. Another vote for false. Another vote for false. And it's, again, really important to make sure, especially as statements get more complicated, because there's starting to be lots of hypotheses here. You want to make sure you sort out in your head what you're looking for when you're looking for a counterexample. So, namely, all of that is part of the if, and then this is the then. So when you go to look for a counterexample, you're looking for something where this whole first part is true. So I'm looking for sets A and B that are both sociable, both finite, and where the intersection has size at least 2. But the intersection is not sociable. Okay. So will someone volunteer for me and offer a counterexample here? I see lots of excellent counterexamples here. So something of this sort. I see a lot of variations of this, but something of this sort will work, where A is sociable because it contains 3 and 4. B is sociable because it contains 1 and 2. But then A intersect B is just the set 1, 4, and it is not sociable. Okay, so this is not true, and this is a counterexample. And every volunteered counterexample in the chat, they're all sort of variations on this, and they're all true as well. Sorry, by that I mean they're all valid counterexamples as well. Okay, that's what I wanted to do for class today, is to go over that. For now, I'm going to swap this over to office hour mode. So in particular, during office hour mode, I am happy to entertain questions about the quiz, the homework, any other thing. So any questions you have, it is free-form question answering time. And I will be here as long as there are questions. But if you don't have any questions and you are ready to go, you are welcome to log on off, or you're welcome to just hang around and see what other questions people ask. Also, I may or may not be having connectivity issues. So if someone could let me know in the chat if you can still hear me, that would also be helpful. Excellent. Excellent, excellent. It occasionally happens that, like, while I have the webcam running and I'm talking, that it decides to disconnect for some reason or another, and I'm always afraid that I'm going to keep talking and no one's going to be able to hear me for an indefinite period of time. So good to hear that it is still there. 3B on the quiz. Yes, I can go over 3B on the quiz. Oops. Okay, so 3B from the quiz. Was to look at the set 2, 4 and asked you to calculate A minus Z. Okay. By definition, this is the set of things that are in A that are not in Z. That's just the definition of set minus. And so I think it's helpful to, when talking about intervals, to draw a number line. 2, 3, 4. And so A itself is all of these numbers, right? So A includes everything between 2 and 4. And note in particular, A definitely contains lots of things that aren't integers. A lot of people are tempted to sort of think, oh, well, 2, 3, and 4 are the only things in this set, so I'm going to just throw those away and be left with nothing. But there's lots of stuff like pi and e, for example, are both in this set. Okay. But when I go to write down A minus z, how's that? Is that less blurry? So when I go to write down A minus z, I'm supposed to throw out 2 and 3 and 4. All of these are supposed to be gone. So in like calculus-y notation, I'm supposed to put like an open circle on each of these places to say that they're not in the set. So A minus z then is, well, there's a pretty natural way to write this, which is to say it's the numbers between 2 and 3, but excluding 2 and 3, union, and then the numbers between 3 and 4, but excluding 3 and 4. So this is what I was imagining people would write as the answer here. And this is probably the most common way people wrote this. Does that make sense, Greta? Okay, yeah, so let's look at 3e. And to the yes-no question that Thomas asks, yes, x or y is positive is the negation of neither x nor y is positive. Okay, 3e asked if this was true or false. X in A. Such that x minus y is in Z. Okay, here again, A is still the set 2, 4, and here B is the set minus 3, 3. Okay. So let's try and parse this for every there exists. And so the thing I recommend is sort of start at the outside and pick your favorite A. So my favorite A is probably pi. So what does the statement say if x is pi? Well then, it would say there exists y in B such that x minus y is in Z. Sorry, such that pi minus y is in Z. Okay. And so I have to decide, is this statement true or false? And I'm not talking about the grander statement. I'm just talking about this statement for x equals pi. And here is, I think, the problem. This statement is true. And why is this true? It's true because I can find some y in B, so that makes this true. So for example, if I chose, say, y equal 2.14159 dot dot dot, then pi minus y is 1, which is in Z. Okay. And the key thing here is that this is a there exists. And so in order for it to be true, I only need there to be one y out of all the y's I could possibly choose that will make this work. Does that make sense? And this is the complexity of what happens when you're sort of looking at a for every there exists statement. So there is one reason you could not pick y equals pi, and that is that pi is not an element of B. But if B happened to contain pi, then you could absolutely pick pi. So would it have been easier to define y as pi minus 1? It depends on what you mean by easier. It certainly would have worked. Do we have to just give one example? No, we definitely do not have to give just one example, because the outside statement here, so the inside statement, for x equals pi, we only have to give one example to show it's true, because it's a there exists statement. However, for the outside statement, this for every piece, we need to show that it actually really works for every x in A. Or at least argue it convincingly in this instance, since it's a little before we had talked about proofs. But you have to argue that this really is possible for every x in A. And it is actually possible. The statement's actually true. So most people wrote something that amounted to saying, uh, is okay. So something like this is not quite a proof, but certainly was sufficient for me to give you credit for knowing what was going on. Morally speaking, it was just people giving me an outline of what a proof would look like without necessarily the formal structure of how we would write this kind of proof this week. Are there other questions from the quiz or homework or life, the universe, and everything that we want to talk about? Yes, that's correct, Kratib. All right, I'm going to hang out here for a bit. Let me know if more questions arise. And remember, as always, I have more office hours tomorrow, so if more stuff comes up, you're welcome to ask then as well. Uh, I would say so. Let is a perfect synonym for suppose. So we're going to talk about proof by cases in a bit. And so we're going to use case in a slightly different way. People would probably know what you meant, but I would not use case in that sense. I'm going to go ahead and wrap up my office hours here for today. If you have more questions, though, feel free to email me. I'm actually just going to go and start recording videos for next week, so I should be around. And and remember, I do have office hours tomorrow again at 11. So definitely come back if you have more questions. And if not, I will see you on Wednesday.